Hi there, and welcome to our lesson on the double angle identities in trigonometry. So we're going to talk in this lesson about what is a double angle and what is a double angle identity, and what are the double angle identities for sine, cosine, and tan. And we will also give a little bit of, provide a few examples of how you might use them. Okay, let's get started. So what do we mean when we talk about the double angle identities? Well, we can just start with the idea of a double angle. Usually when we talk about a trig ratio like sine, we're talking about something like the sine of A or the sine of X or the sine of theta. It's possible that you might have a double angle. So instead of talking about the sine of A, maybe I talk about the sine of 2 times A, the sine of 2A. Now the double angle identity that we're going to discover in just a minute for sine is actually that sine of 2A is 2 times the sine of A times the cosine of A. And we'll see why that's true in a minute, and we'll also look at the ones for cosine and tan as well. So it gives you a way basically of going from a double angle to a single angle. Now how we use that isn't obvious to start. It's very useful when we go to solve trig equations, which we'll get into a little bit later in the course. But for now, we could demonstrate this law. One thing we could say is we'd say 20 degrees, for example, could be thought of as a double angle because it's double 10. So we know that the sine of 20 degrees is 2 times the sine of 10 degrees times the cosine of 10 degrees. Don't know how useful that equation is. If we don't know what the sine of 20 degrees is, we probably don't know what the sine of 10 degrees is either, or the cosine of 10 degrees, but that is true. Another thing that we could use to illustrate is we know the sine of 30 degrees is 1/2, and we also know that the cosine of 30 degrees would be √3/2 from our special triangles. So we could use those to find the sine of 60 degrees. Since sine of 60 degrees is 2 sine 30 cos 30 from the double angle identity, which is 2 times sine 30 1/2 cos 30 √3/2. 1/2 times 2 is 1, and sure enough we get √3/2. Now this is just demonstrating that the rule works. We know the sine of 60 is √3/2. We shouldn't need to use this 30 degrees to calculate it, but we certainly can. Let's take a look at why this equation here, why it is true, and that's our next question. So let's look at how we derive the double angle identity for sine. The key to this is actually to remember that we know the addition identity for sine. That sine of A plus B is equal to sine A cos B plus cos A sine B. And the reason that's helpful is if we look at sine 2 theta, that's really just sine theta plus theta, and applying the formula that I've written down for you on the side gives sine theta cos theta plus sine theta cos theta. And since those two terms are the same, that makes them like terms, we get 2 sine theta cos theta. And there it is. And we can make that conclusion that sine 2 theta is 2 sine theta cos theta. How about the double identity for cosine? If there's one for sine, there's almost certainly one for cosine, and we can derive that identity in a very similar manner. We know that cos 2 theta is really cos theta plus theta, and so we think about the addition identity for cosine. There's the cosine addition identity. Cos A plus B is cos A cos B minus sine A sine B. You could probably pretty much finish this derivation on your own. Okay, I get cos theta minus sine theta, or cos squared theta minus sine squared theta. Now, there's some things that we can actually do with this formula. Remember, we know Pythagorean identity, that's that sine squared theta plus cos squared theta always equals 1. which means that anytime you have a sine squared theta, you could replace it with 1 minus cos squared theta. And every time you have a cos squared theta, you could replace it with 1 minus sine squared theta. So we can actually take this equation here and we can rearrange it a bit by first replacing cos squared theta with 1 minus sine squared theta. And we come up with the same identity, but just written differently, 1 minus 2 sine squared theta. So cos squared theta minus sine squared theta can also be written as 1 minus 2 sine squared theta. Now, why did we replace the cos squared theta and not the sine squared theta? I don't have a good reason. There's no reason why you couldn't do it the other way around. So we get yet another formula. If we replace sine squared theta with 1 minus cos squared theta, we get 2 cos squared theta minus 1 for our third double angle identity for cosine. So our conclusion here is that there are actually 3 different double angle identities for cosine: cos squared theta minus sine squared theta, 1 minus 2 sine squared theta, or 2 cos squared theta minus 1. I mean, they're really, all of them really are the same identity, just rearranged differently. It tends to be, I mean, you might end up memorizing them all without, just because you use them enough, but you can always, if you have one of them, you can always get the other two just by replacing cos squared theta or sine squared theta with whatever you want. And we'll use different ones at different times depending on what we're doing. Next, we'll look at a simple example of using the double angle identities. Now, I think the real use for double angle identities is when we're solving trig equations, and we're going to cover that shortly in this course. But for now, we'll look at a few things you could do. So I see this 2 sine 3 pi over 8 times cosine of 3 pi over 8, and I notice what that looks a lot like. Remember that 2 sine x cos x is equal to 2 sine x. Is equal to sine 2x. The double angle formula for sine, I've just used x instead of theta. I could use a or whatever I want, it doesn't matter. So I look at this and I say here my x is like 3 pi over 8, and I have the left side of this equation right here, which means I can replace it with the right side of the equation. Instead of sine 2x, I have sine 2 times 3 pi over 8. Well, of course, that's the sine of 3 pi over 4. That is one of those special angles. We can actually figure out what that would look like. So 3 pi over 4 would be 3/4 of pi is an angle in the second quadrant. With a related acute angle of pi over 4, which gives us the 1, -1, √2 triangle. Okay, and so sure enough, sorry, that's kind of a mess, but we can see that okay. So sure enough, that's supposed to be a pi over 4 there. The answer is 1 over √2, which reduces to √2 over 2, or simplifies to √2 over 2. Now you might say, well, you were only able to do this question because you happen to have this, this 2 right here. Okay, and if the 2 weren't there, then it doesn't work because it doesn't look like the left side of the this equation here. But we don't actually need the 2. I could have just had sine 3 pi over 8 times cosine of 3 pi over 8. And actually having a sine of an angle times a cosine of an angle is actually pretty common in math and calculus and other subjects. That actually happens quite a bit. So in this case, what would we do? Well, we could look at it and we could just say, okay, well, this is, instead of having the left side of the equation, 2 sine x cos x, we have half of that, which just means we have half of sine of 2x, and x, of course, being 3 pi over 8 here. I mean, another way, an even simpler way of looking at it is, look, if we were able to figure out 2 times the sine of 3 pi over 8 times the cosine of 3 pi over 8, then we can figure this out because it's exactly half as much. So sure enough, we will get exactly half of sine 3 pi over 4, half of √2 over 2. which is, of course, root 2 over 4. So we don't actually need that 2 out there. We can still adjust it by putting a half there. For our next question, we are given the ratio for the cosine of x, that it's negative 2/3. And our job is to figure out what sine 2x and cos 2x would have to be. Well, I think that the easiest thing to do to start is to realize that if we have the cosine of x, we can always calculate the cosine of 2x using the double angle identity for cosine. You can use whichever, remember there are 3 of them, you can use whichever one you want. So I'm going to use this one right here. Okay, it makes sense to use this one right here because this is the only one that doesn't involve sine. I don't have sine right now, I just have cosine. So cos 2x is 2 cos squared x minus 1. Well, if cos x is negative 2/3, then we're going to square that, multiply it by 2 and subtract 1. Negative 2/3 squared, it's 4/9. 2 times 4/9 is 8/9, and take away 1 would give you negative 1/9. So that's the easy part of the question. The more challenging part of this question would be, how do I figure out what the sine of 2x is equal to when I don't have sine? Well, I mean, the only thing I know is that sine 2x is 2 sine x cos x. I have cos x, but I don't have sine x. Well, we can figure out what sine x has to be. Because if we look at what we're given here, these two pieces of information here, the cosine ratio, followed by the interval that the angle is on, the angles between 0 and pi, lets us actually draw a picture to figure out what sine would have to be. So if cosine of x is negative 2/3, can we draw that? We definitely can. We know the angles between 0 and pi, so we know it's in quadrant 1 or quadrant 2. Well, if it's a cosine and it's negative, keep in mind cosine is x over r, it must be that it's in quadrant 2. It can't be in quadrant 1. Obviously, cosine is positive in quadrant 1. Remember the cast rule. So it's over here. This is our angle. Okay, and we have, let's see, we have our adjacent side here, must be negative 2. And our hypotenuse is 3. And then we have the opposite side too, or the y value, our x value is negative 2. Now we can actually use Pythagorean theorem to figure out what this missing side would have to be. Let's do that. So I've called that side y, which is of course appropriate, and Pythagorean theorem tells us that 3 squared equals y squared plus negative 2 squared, or positive 2 squared, doesn't really matter what you do. That gives you 9 equals y squared plus 4, or y squared equals 5, or y is the square root of 5. And we know that y is positive here because of this picture. Notice that that tells us, by the way, so this is our angle x that we've drawn here. Angle x. That tells us what the sine of x has to be. The sine of x must be equal to root 5 divided by 3. Now, hopefully you notice that without this information about the angle being between 0 and pi, we wouldn't know that it was right here. Another possibility, if cosine of x is negative 2/3, it's also possible that your angle is down here in quadrant 3, in which case your y value would actually be negative root 5. And we'd have an entirely different answer here. There'd be 2 answers to this question. So limiting this little hint basically changes the question, so there's only one possible answer. And let's take a look at that answer right now. So the sine 2x equals 2 sine x cos x. So in this case, we figured out that sine x is root 5 over 3. Of course, we know cosine is negative 2/3. And that gives us negative 4 root 5 divided by 9. How about a double angle identity for tan? Well, I think this is actually a great exercise. If you want to try to derive this yourself, you can do it in a similar manner that we did for sine and cosine. So feel free to pause this lesson and take a look at it yourself if you like, before I give you the derivation. Okay, well, to start with, tan 2 theta is tan theta plus theta. And so we can use the addition identity for tan to answer this question. This is one way to do it, by the way. There are other ways to do it. So if you remember, the tan of A plus B is equal to tan A plus tan B all divided by 1 minus tan A tan B. Okay? And that is actually going to give us a nice identity, because it's, I guess I should have said this, but it'd be nice if the double angle identity for tan only involves the tan ratio in its answer and not sines and cosines. I'll show you what I mean at the end. Okay, so just using this formula right here and filling in A and B are both theta, I get tan theta plus tan theta, 1 minus tan theta times tan theta, or 2 tan theta divided by 1 minus tan squared theta. There is your double angle identity for the tan ratio. Now, if you're deriving that yourself, there are other ways to do it. Instead of doing it this way, if you had wanted to, you could have said that, I'll show you how we do that a different way. You could have said tan 2 theta is equal to sine 2 theta over cos 2 theta. And from there, said that that is 2 sine theta cos theta divided by, let's go with cos squared theta minus sine squared theta. And maybe you would even stop there and say that's the identity, and it is, but it's just not as nice as having one that's just in terms of tan. So the way that we can actually make this in terms of tan is we can actually divide the top and bottom of the equation, or the fraction, by cos squared theta. And when I do that, I end up turning everything into a tan ratio. Let's see how that works. I take cos squared theta and divide it by 2 sine theta cos theta. So what ends up happening is you get 2 sine theta divided by cos theta, because of course the cos theta divided by cos squared theta, the cos theta on the top will divide out, and on the bottom, cos squared theta divided by cos squared theta is 1, and sine squared theta divided by cos squared theta, just like that. And of course, sine theta over cos theta is just tan. So you end up getting 2 tan theta over 1 minus tan squared theta, just like we had up here. So there's another way to derive the same formula. And that concludes this lesson. So thanks for tuning in, and I'll see you next time.